Hello students, welcome to Beranker. This is Joyjit Sir here from Physics Department. So today we are going to discuss a very important topic for the NEET JEE batch 2026, the kinematics. We include motion in one dimension and motion in two dimension, both the chapters from NCERT in this unit, kinematics. For your convenience, the whole topic, which is the whole kinematics part, which is very large actually, and it has several subsections. So we have divided the whole topic, all the topics of kinematics for you in a few parts. So today we are going to discuss the part 1. In this part, what we are going to do, we are going to discuss the nature of graphs for different motion quantities. We have 5 motion parameters basically, displacement, distance covered, or the path length, x can be taken as both of them, the velocity, the speed and acceleration. We will show in this part how do they vary with time or with one another. Like what does the VT curve, velocity time curve look like, what does acceleration versus position, what does velocity versus position curve look like, and etc, etc. This part, the kinematics, actually requires a knowledge of several sections of mathematics, like the algebra, like the coordinate geometry, and obviously the calculus part, the both differentiation and integration. So along with the class, as we progress, we will discuss a few topics from mathematics. There are many students who do not take mathematics as a subject when they as for their academic study. So basically, when we are going to discuss this kinematics part, since we are required to know mathematics a lot, so we will discuss the topics of mathematics as per the requirements of the topic and whenever and when it is necessary. So let's start the very important part for NEET JEE, the kinematics. And welcome all the students. I welcome the Joyjit Sir, welcomes all of the students, all of the NEET JEE aspirants for 2026 to this part, the kinematics. The Beranker, we build better for you. So let's start. So what topics we are going to discuss today? Let's mention them first. In this topic, in this class, today's class, we are going to discuss first the nature of different graphs. First, we will understand what graph looks like what. Nature of different graphs. And then we are going to discuss a few applications of our knowledge in physics. Application in analyzing, motion in our subject physics. So first, let's start with shapes of different types of graphs. We will need this knowledge of coordinate geometry at first. First, we will learn the shapes of different graphs, and first we will learn the graph of equation y equals to x to the power n. Depending on the power of n, the graph may take different shapes. First, let's learn what does the shape of y equal to x to the power n look like when n is a integer. X, y, this is negative y axis, this is negative x axis, Now, if n has even power, that is, if n is an even integer, the graph would look like somehow this. Because for even powers, whatever be the value of x, that is if x is greater than 0, since n is even, y equal to x to the power n would be greater than 0. And if x is less than 0, that means negative y equal to x to the power n is also greater than 0. It cannot be negative because the power is even. Now one more thing, if the power is 2 or 4 or 6, how do you show them in the same graph? Let's understand that. As n increases, the graph shifts towards the right. So I will show you by the yellow color the graph of y equals to x square. The graph looks like, say, this. Obviously it will assume a parabola. We call this a parabola. Now if y becomes x to the power 4, the graph will shift towards the right more. That is, graph will be more widespread. The more the power, the more widespread the graph is. So like this. If you take y equal to x to the power 6, the graph will be more widespread, like this, and so on. So as the power increases, y equal to x to the power n becomes widespread more and more. The next thing, of course, we will discuss what does the graph look like if the power is, odd, that is 1, 3, etc., etc. So if x dash, y dash. You can clearly think of this fact, since x is now negative, so the graph has its part in the first quadrant and third quadrant. When the power is positive, y equal to x to the power n greater than 0, which means the graph has only its part in first and second quadrant. You see? But if the power is negative, if x is negative, for negative values of x, y equal to x to the power n will have its part in the first and second quadrant. In these cases actually. So when x is positive and x is negative, the graph in both cases have positive values of y. So the graph lies in first and second quadrant. Remember this. But if the power is negative, later on the power, if the power is odd, integer, that is if n equals to an odd integer, then what happens? Then for x greater than 0, y equals to x to the power n will be greater than 0. And if x is negative, that is less than 0, then y equal to x to the power n will also be less than 0. So the graph has its part in first and third quadrant. So the graph will look somehow like this. This is the part in the first quadrant. This is the portion of the graph in the third quadrant. For different values of n, when n increases actually, the graph becomes more and more widespread. But remember, if n is 1, odd integer means n can take values of 1, 3, 5, etc., etc. Except for 1. When n is 1, so we can exclude 1 from this graph, because if n is 1, the graph assumes a straight line form. Like this. X prime, y and y prime. The graph looks like this. If this is the graph of y equal to x to the power n, of course, but n being 1. So you can say this is the graph for y equal to x, n being 1. But if n takes other powers, then the graph will look like the shape. Suppose we want to figure out how y equal to x cube looks like. This will be the shape for y equal to x cube. Now, if the power increases, the graph becomes widespread. We already know that. So, if y equal to x to the power 5, the graph will assume this form. If y equal to x to the power 7, the graph would assume this form. And so on. Okay. So, we have discussed the graphs for y equal to x to the power n with n is an even integer. Remember, here in all these graphs, n is odd or even, but n has been taken to be a positive integer. So you can say these forms n is even, positive integer. And here n is odd, positive integer. But what happens if n is negative? Let's discuss a few of them. We will not generalize this part because not all negative powers are required for us. We will just discuss a few of them. Like y equals to x to the power minus 1 or y equals to 1 by x. You all know that this graph will assume the shape of a hyperbola. It's a hyperbolic relation. So in this case, the graph would look like this: x, y, x prime, y prime. This is its part in the first quadrant. This is its part in the third quadrant. Okay. If power is negative, then this will happen. Not many more powers are required in this case, so we are not interested in them. Now what happens if n is not an integer, n is fraction? Then what happens? How it might look like? Like say you want to plot y equals to x to the power 3 by 2. You can see the power 3 by 2, that is 1.5, lies between the values 1 and 2. So of course 1 corresponds to the graph of y equal to x, 2 corresponds to the graph of y equal to x square. So the graph will lie between the shape of x and x square. So now you can plot the graph like this: x, x prime, y and y prime. Y equal to x is a straight line like this, and y equal to x square is the parabola, the yellow parabola in these graphs. So the graph will lie somewhere between them, like not a parabola, but like as such. Okay. This would be actually a straight line. The graph will look like this. You can also say it good with, when you compare it between the powers of 1 and 2, it looks more familiar to you. So this is the graph of y equal to x. This is the graph of y equal to x square. This will be the graph of the sky colored graph. Is the graph would be is the graph of y equal to x to the power 3 by 2. So the graph lies between the shape of the powers 1 and 2. Okay. Now suppose you want to plot 3 curves at the same time: y equal to x, y equal to x square, and y equals to x cube. How does it look like? How does it look like? Let's figure out. X, x prime, y, y prime. The first graph, y equal to x, will be a straight line like this. The second graph, y equal to x square, it will be like this. This particular value is x equal to 1, y equal to 1 value, where all the 3 graphs will intercept. Y equal to x cube will be more widespread. This is y equal to x square graph. Y equal to x cube would be looking somehow like that. More widespread, but they will intersect all at the same point, 1, 1. Because when x equal to 1, y equal to x will be 1, y equal to x square equal to 1, y equal to x cube will also be 1. So all the three graphs will pass through the point 1, y equal to x equal to 1. This is the common intersection points of all the three graphs. Okay. Now, if the power is negative, we already discussed one negative power, y equal to x to the power minus 1. Other negative powers will have like similar impact. Like if you want to plot y equal to x to the power minus 2, that is 1 by x square, which is very common for field forces. I can give you an example like the Coulomb force, the gravity force. All they vary with the distance r like this, proportional to 1 by r square. So these graphs would assume this shape as well. So F versus R graph, force versus distance curve, all of them will be assuming this shape. Okay. This shape is almost similar to y equal to x to the power minus 1 case, that is this one. But that was a hyperbola when power is minus 1, x to the power minus 1. For other powers, you cannot say it's a hyperbola, but it will be somehow like that. Now let's study a few more graphs, which is of our importance. Like y equals to e to the power x. Suppose when x occurs at the exponent, that's the exponential curve. When x equal to 0, y equal to 1. So this graph cuts x-axis at the point x equal to 0, y comma 1. Sorry, y-axis. And it will be exponential for x with, if x has a large value, then y is also large. And if x equals to, if you study other figures for x and the y, when x is say minus infinity, the y will be. So this graph extends towards this, and for any power of x, this graph cannot have any negative value. Whatever be the value of x, for any x, y is always greater than 0. Only at x equal to minus infinity, the graph can lie at y equal to 0 point. So y is always positive for the graph. And it cuts y-axis at this point, 0, 1 point. So if this is y, y dash, x and x dash, combining all the features, the graph would look like this. This is the exponential nature of the graph. Okay. And if y equals to e to the power minus x, the scenario is reversed. Here you can say for x equal to 0, y is again 1. This value is actually y equal to 1 by e to the power x. And if x tends to infinity, here also you can give this sign, y tends to 0. So as the value of x increases, the graph goes towards 0 value of x. And also it cannot have any negative part, because for any value of x, all values of x, y is always positive. For any x, y is greater than 0 also. So if that is x, there is y, the graph passes through this point, 0, 1. And it looks like this. It starts from a positive, very high value of y, and x tends to infinity, the graph tends to be 0, but it never touches the x-axis. There are other shapes that we can talk about, like if you have this function y equal to 1 minus e to the power x, then what happens? At x equal to 0, y is 1 minus e to the power 0, that is 1 minus 1, that is 0. For x any value greater than 0, see, y is negative. If x has any value greater than 0, e to the power 1 or e to the power 2, etc., all of them will have a value greater than 1 because e itself is greater than 1. So the graph now would assume this shape. I'm going to show you. This is x, this is x prime, this is y, this is y prime. And how does it look like? The graph passes through the point 0, 0. See here, when x equal to 0, y is 0. And then for any positive value of x, y is negative. See, for any positive value of x, y becomes negative. And x becomes higher and higher, y tends to be infinity. So the graph would look like this. Oh, and for any negative value of x, if x is less than 0, then y equal to, say, x is minus 1. So y is 1 minus 1 by e, which is of course positive. So for x less than 0, the graph is positive. For x greater than 0, the graph is negative, then y is negative, and it passes through 0, 0 point. And it's exponential curve, so it goes towards very large value of y when x is large. So the graph would assume this shape. X becomes less than 0, y tends to 0 as well. So the graph would look like this exponential curve. On the other hand, if y equals to 1 minus e to the power minus x, you can see for x equal to 0, the graph again is 1 minus e to the power 0, that is 1 minus 1, that is 0. So for x equal to 0, y is 0. For x equals to 1, y equals to 1 minus e to the power minus 1, that is 1 minus 1 by e, which is of course positive. And if x takes a very large value, x tends to infinity, then y equals to 1 minus e to the power minus infinity, that is, this value is approximately 0, so y tends to 1, you can say. So this is x, this is y prime, this is x prime. Now look at the shape of the graph. It passes through again 0, 0 point. As x is 1, y has the value 0. So let's plot out this point. This is 1, 0. And when x tends to infinity, the graph is 1. The graph appears to have the value of 1. So x tends to infinity, this is the value of y equal to 1. So the graph will assume this shape. It tends to be, the value of y tends to be 1 as the graph rises to the right. It will assume this shape. Actually, initially it rises very fast, then it takes this shape, asymptotic shape. Okay. Now, if a few more graphs, we have already learned what does y equal to x look like. Y equal to minus x, it will be a mirror image of y equal to x. So x prime and y prime. This graph looks like this one. When x is positive, y is negative here, and when x is negative, y is positive, and when x equal to 0, y is 0. The graph bears all these properties. So these are the basic shapes of the graph of y equal to x to the power n. Although from in this part we have discussed the shape of y equal to e to the power something like, so you can say this portion is the discussion for exponential graphs. Exponential graphs. Okay. Now, a particular graph of straight line, basically depending on the equation y equal to mx plus c, that's that form. That's very important. We will require this knowledge to analyze problems in physics. Straight line can be expressed in many a way. There are many ways to express the equation of straight line. One equation has this form. It's called the slope intercept form. This is very important in physics to analyze the linear graphs. Let's see how does it look like. It can take, of course, very many different shapes. You all know already in which direction I am showing x and in which direction I am showing y. So from now on, I will stop mentioning x and y axis. You already know that horizontal is x, the vertical is y. So a general equation for y equal to mx plus c could be like this. Say this could be one form of y equal to mx plus c. This graph has 2 points of intersection, this and this. In y equal to mx plus c, if you put x equals to 0, y is c. So this point can be taken as 0 comma c. Here c is called the y-intercept. That is the length of the portion the graph intercepts from the origin. Y-intercept of the graph. And if you draw a line parallel to x-axis in this graph, this is the x-axis, we draw a parallel line. So the graph makes an angle theta with positive x-axis. The theta is called the slope angle or inclination. Remember, inclination of a graph is always measured with the x-axis. And the m thing in this graph, y equal to mx plus c, the m, what does m stand for? M is the value of tan theta. The tangent of theta, it's called the slope of the graph. So depending on the values or the range of values of theta and c, the graph can take different forms. This is the general form. We will show you what might be other forms of the graph. The graph we just showed, I'm taking it again. This is the graph. You can see actually that in this case, in this graph, theta is less than 90 degree. That is acute angle. So m, which is tan theta, will be positive, because when theta is 90 degree, the acute angles, it lie in the first quadrant, and from all sine tan cos rule, in the first quadrant, tan theta is positive. So here the slope is positive, you say. So when the graph makes an acute angle with positive x-axis, we say its slope is positive. And also the y-intercept is positive here. We have 2 points to understand. You can see the c here, the y-intercept, c is positive. So when c is positive and m, the slope is positive, the graph will take this form. Look at this graph. Here also theta is acute. So you can directly now say that m will be positive, because for acute angles of inclination, the slope is positive. But what about c? You see, c lies towards negative y-axis. So this is the c, y-intercept. So here the y-intercept, you can clearly see, it's less than 0. The y-intercept is negative here. There might be two other forms of this graph. If the graph would assume this form, however, take a look. This is the C, y-intercept. But look at the angle of inclination. This is the angle of inclination, theta. So again, you can clearly see here that theta is now greater than 90 degree. That is, theta is an obtuse angle. So the slope, that is tan theta, would be negative. These types of slopes are called negative slopes because when theta is greater than 90 degree, the angles lie in the second quadrant, and we know in the second quadrant tan theta is negative. All sine tan cos rule in the second quadrant, sine and subsequently cosec are positive. All other t ratios assume negative values. So here the slope is negative, and the y-intercept C, it is positive. It's clear. Now the last type of shape, the fourth type of shape, if this is the graph, then again you can see that is theta, and this is the y-intercept C. So here theta is greater than 90 degree again. Since theta is 90 degree, you will directly say that M is negative. This graph has also the negative slope, and C is less than 0. Y-intercept is negative. So depending on M and C, the slope and the y-intercept, the graph of y equal to mx plus c may have different shapes. One more thing is of importance for us. I mean, one more shape of graph is important for us. It is also straight line. But as I said, a straight line can be expressed in many different ways. One of the way is this, expressing an equation of a straight line like this: x by a plus y by b equals to 1. This form is called, intercept form. How does it look like? If this graph may also have different shape, if A, that is y-intercept, and B, that is, if x is, A is the x-intercept here and B is the y-intercept here. So if A is greater than 0 and B is also greater than 0, then the graph will intercept x-axis at the point a, 0 and y-axis at the point 0, b. Joining the 2 points, we get the graph. The shape would be like this. Analyzing A and B, you can also, determine how the other variations of this graph, of this straight line, may look like. Like if A is greater than 0, but B is less than 0, then you can say the graph will intercept x-axis at a, 0 and intercept y-axis somewhere here, because B is negative, 0, minus B. And you join these two lines. This will be the graph this time. If A is less than 0 and B is greater than 0, then the graph intercept x-axis at any negative portion, say minus a, 0, but y-axis at a positive part, which is 0, b. Joining these two lines, you get the shape like this. And lastly, if A is less than 0 and B is also less than 0, then the graph will intercept x-axis and y-axis like at minus a, 0 and at 0, minus b. If you join these 2 points, you will get the fourth variation of this straight line. So by looking at the graph, now you can determine in which form it is given, and you can identify A and B from there. This is the graphical portion. which are required for us for our study in physics to analyze the nature of different graphs. How does a graph look like? Now a few notes on them. In the equation y equals to mx plus c that we discussed earlier, if c equal to 0, then the graph will assume this form only, y equal to mx, and it will be a graph through origin. So remember, whenever the constant part is 0, the graph will pass through origin. You have to remember this section, this line. Of course, it may take different forms depending on m. So if m is positive, the graph will have a positive slope like that. If m is negative, the graph will have a negative slope like that. But in either cases, it will pass through the origin because c is 0. A few more notes. What happens if y equal to constant? For any values of x, if y is constant, then the graph will be a line parallel to x-axis. And if x is constant, the graph will be a line parallel to y-axis. So I will show them in the same graph. Y equal to constant is a graph like this. This is x, this is y-axis. This is the graph for y equal to constant. And if x is constant, the graph might be like this. Here x equal to constant. Of course, here we have taken the constant is positive. If the constants are negative, then the graph should be on the other way around. Like this is also graph of y equal to constant, say c, but this time c is negative. And this will be the graph of x equal to constant, where the constant is negative. In all these cases, we have taken this point as origin. So these are the basics of all the graphs, although we will encounter a few more types when we solve problems on these topics. But these are the basic shapes that you have to remember whenever you are going to analyze the graphical questions or tackle the graphical questions in physics. Okay. Now, we have to learn calculus a bit also before we start analyzing problems of physics. First, let's take a look at differentiation process. You know the basics although. What is differentiation? You know the deal. If y is a function of x and delta x tends to 0, then delta y to delta x, that is the ratio of change in y, variation or increment in the y to the increment of x with limit delta x tends to 0, is called the derivative of y with respect to x. So whenever we encounter very small changes, we can deal with the differentiation process. But change should be very small or instantaneous. So in most of the cases, when we are talking about instantaneous power, let's start with instantaneous velocity. You want to find out instantaneous velocity, you want to find out instantaneous acceleration, you want to find out instantaneous force, you want to find out instantaneous power, etc. In all these cases, calculus will be your tool whenever you are going to find out instantaneous figures. Instantaneous means at a given point or at a particular point or space, at a particular time point or at a given space. Like a particle is moving, you want to find out its velocity at a given point x equal to 2 meter. That means its instantaneous velocity, you have to apply calculus. Suppose a particle is moving so that its acceleration is varying with time. You want to find the acceleration at t equal to 1 second. So then calculus will be your tool because we want to find out instantaneous acceleration. The language of physics is very important to understand. They will never say find out instantaneous acceleration, find out instantaneous velocity. You have to figure it out yourself. Whenever in the question they are talking about any quantity, finding out any quantity at a given point of time or at a given space or given location, calculus will be your tool because you are trying to find out the instantaneous values. And whenever you are going to find out the values within a range, then they are talking about average quantities. Then integration can be your tool. That means again calculus, or sometimes averaging process will be your tool, or sometimes there is definitions for average quantities. So the basic derivatives that we may want to deal with for most of our graphs are like this. If y equals to sine of mx, m can be any integer, then dy dx, that is d dx of sine mx, would be m cos mx. If y equals to cos mx, however, then derivative of y with respect to x, that is d dx of cos mx, would be minus m times sin mx. We don't have to know other t ratios for now. If we have an algebraic function y equal to x to the power n, then dy dx, that is d dx of x to the power n, would be nx to the power n minus 1. If you have y equal to ln of x, where ln stands for identical to writing logarithm to the base e, the natural logarithm, then dy to dx, that is d dx operator of ln x, would be 1 by x. And if y equals to e to the power mx, then dy dx, that is d dx of e to the power mx, will be m times e to the power mx. These will do for us for at least NEET JEE preparation. We don't need much here. These are the basic differentiations. Now, in notes, a few notes should be made on the basic theorems on differentiation. Number one of them, derivative of two functions fx and gx, if they have a sum or difference, can be found out by taking derivative of each of them individually. So d dx of sum of or difference of two functions fx and gx would be d dx of fx plus or minus d dx of gx. You know that. If there is a product of two functions u into v, where u and v both are functions of x, say u equal to fx and v would be gx. This can be found out by finding this u, one function constant, derivative of other, u times dv dx plus v times du dx. Number 3, derivative of ratio of two functions u to v would be v square times first v into du dx minus u times dv dx. You cannot change the order here. You cannot take u dv dx minus v du dx. You have to always take v du dx minus u du dx. So you have to understand clearly the numerator and the denominator. And one more property, it's a very important property. You cannot say it's a theorem, but it's a property. Suppose you want to take derivative of a function which is another function of x. What will be this derivative? F of gx. This will be the derivative of the whole function of f, that is, you can mark it by f dash of gx. So take derivative of whole function times you take derivative of gx as well. So derivative of the f function times derivative of the g function. And one more thing, if you want to take derivative of a function which is not a function of x, rather another variable, say you want to take ddx of a function which is a function of time, you cannot do it directly. You have to first change the operator. Operator will be d by dx. You have to change the variable here. Sorry. So it will be d dt of ft times dx to dt. This will be the process. This process is applicable when the independent variable x and the variable of the function are not the same. If two functions are same, you can take the derivative directly, but if not, then you have to apply this process. You have to change the independent variable for derivative portion and then take derivative of that function with respect to the function of the embedded one, the ft. The variable in embedded one was t. Now, this is the basic theorems on taking differentiation process. Now, what does differentiation allow us to do? So we have to interpret the differentiation process. What does it do actually? Interpretation of the operator d by dx, or rather say the process dy by dx. See, the d dx of y, the derivative of y with respect to x, can be interpreted in two different ways. Number one, it explains the slope of a curve. Suppose this is xy curve where y is a function of x. Say that is the curve. You choose a point on the curve, say P. You draw a tangent on the curve at the point P. Now if the tangent makes an angle theta with horizontal direction, then m, that is the slope of the curve, tan theta, would be given by dy to dx. There is one interpretation of dy dx. So you have xy curve, dy dx would give you the slope of xy curve. If you have xt curve, the slope dx dt will give you the value of dx by dt would give you the value of the slope of xt curve. Whatever curve you have, its slope at a given point will be given by the derivative at that point. One more thing is the rate measurer thing. So in this case, we have taken dy dx, we have interpreted dy dx as the slope of a curve. You have any curve, you want to find its slope, you have two processes. Either you know the value of theta, then tan theta would be the slope, or if you know the function, you take derivative, you will have the curve. The value of derivative will give you the value of the slope. And the second thing is dy dx can also be treated as a rate measurer. Dy dx can be interpreted as rate of change of y with respect to x. That's another interpretation of dy dx. So I would like to cite a few examples here in this case to clarify this. Like you want to find velocity of a particle. You know, velocity is displacement to time ratio. Now displacement can be taken as change of position of a body. So it's change of position. Say body is moving along x-axis. So position will only be varying along x-axis only. In the time interval in which the change of position has taken place. So velocity can be treated as rate of change of position with respect to time. The position is x, time is t. So velocity can be written as dx by dt. But what velocity? Be careful at this section. This velocity is instantaneous velocity. It's not the average velocity. Instantaneous velocity is the rate of change of position with respect to time at a given point of time. So this will be given by dx dt. Similarly, you want to find instantaneous acceleration of a body. Instantaneous acceleration can be written as change of velocity divided by the time interval. How much velocity has changed in a given time interval. So it's really rate of change of velocity v with respect to time t. So instantaneous acceleration can be written as derivative of v with respect to t, dv by dt, because rate of change of y with respect to x is dy dx. So rate of change of v with respect to t would be dv by dt, rate of change of x with respect to t would be dx dt, and etc. so on. So here we have already defined two quantities of physics, instantaneous velocity and instantaneous acceleration. Now the reverse process of differentiation in calculus is called the integration. What does integration do? Integration can also be treated in two ways, but first we will learn how to integrate. What is the definition of integral? We can define it in two different ways. Number one, as an inverse process of differentiation. Inverse of differentiation. In this case, the integration or the integral is called indefinite integral. This definition says if d dx of fx is gx, then integral of gx with respect to x, that is gx dx, will be fx plus c. Here c is called the integration constant. So and the other definition defines integration as area of a curve. This is identical as defining integral as sum of an infinite series. Defining integration as a sum of infinite series is not of our particular interest in physics. That's the process of mathematics that is required in mathematics. So we will only limit ourselves to defining integration as area of a curve. In this method, we first take a curve. Say this is the curve of y equals to fx. We choose two values on the point for two different values of x. Say here x equal to x1 and at this point x equal to x2. Now area of a curve for sum of an infinite series is called the definite integral. The definite integral is always taken between two limits, here the limits being x1 and x2. So if we have this y equal to fx curve and you want to find this area particularly, then the area is defined as integral of fx dx equal to the area between the limits x1 and x2. Here the one who doesn't have mathematics as their subject can make note of this fact, that if integral of fx dx equal to gx, then integral x1 to x2 fx dx would be, you can say that is gx plus c if you choose. Integral fx dx is gx plus c. If this happens, then integral x1 to x2 fx dx would be finding the value of the integrated function, the gx, from x1 to x2, which is g of x2 minus g of x1. The basic integrals for physics part would be these. Number 1, integral of x to the power n dx. It would be x to the power n plus 1 by n plus 1 plus the c. Integral of sine of mx dx would be minus cos of mx by m plus c. It's a reverse process of differentiation. So during differentiation, sine mx became plus cos mx times m, or plus m cos mx. The integration is reverse process, so sine becomes negative after integration and m is divided, not multiplied. Integral cos of mx dx would be plus positive sine mx 2m plus c. Our integral dx to x, it would be ln of x plus c. Lastly, it's a shortcut actually. Integral of dx would be simply x. I have put n equal to 0 in formula 1. You can also check it out for yourself. That's integral of dx, which is equal to x. These are the basic integrals. Now let's learn an example. Suppose you want to find the value of x square, 2x square, say 3x square, just say, dx within the limit 0 to 1. How do you solve this? The constant terms go out of the differentiation and integration both. Like I forgot to mention it during the integration formulae. Just learn that integral of c times fx dx can be written as c times integral of fx dx if c is a constant. Same process was also true for differentiation. Same process. You can make a note of this here, where we wrote the basic theorems on differentiation. d dx of c times fx, where c is a constant, can be written as c times d dx of fx, where c is a constant. So now the process. 0 to 1, 3x squared dx. 3 goes out of the integration. You have x squared dx, 0 to 1. Now x square integrates to x cube by 3, 0 to 1. It's from the formula number 1. Here n is 2. X to the power n integrates to x to the power n plus 1 by the same power n plus 1. So here we have done this. Now how to evaluate this portion? How to evaluate this x cube by 3 within the limit 0 to 1? First we will put the upper limit 1 there. So it becomes 3 times 1 cube by 3 minus we put the lower limit there, 0 cube by 3. So overall it becomes 3 into 1/3, that is 1. So you do integration like this. So these are the basic integration, differentiation and coordinate geometry that we are required to know before we start the real deal with kinematics. But how do we employ them? Let's learn a few on them. Let's take a few examples actually. How to apply them in physics. I told you for today's class we will learn some basics on graphs and then we will learn how to employ them in physics. Let's learn. Take this question. Suppose position of a particle is 2t minus 4t square plus 10 meter. T is expressed in seconds. There might be several questions on this part. Number 1, here x is the position of the body varying with time. So it means the body is moving along x-axis only. The first question, find velocity at t equal to 2 seconds. How to do this? Find velocity of t equal to 2 seconds. How do we find this velocity? We already defined. Here you have to find velocity at t equals to 2 seconds. It means you have to find the instantaneous velocity. And instantaneous velocity at t equal to 2 seconds would be given by dx upon dt. Velocity is rate of change of position with respect to time. So position is x, time is t. So rate of change of x with respect to t means dx by dt. We have to find dx by dt and evaluate it at t equals to 2. Now take derivative of x. Here is 2t. T has a power of 1. Since nothing is mentioned, no power is there, so it means power is 1. So it becomes 2 times dt by dt. I am breaking down the process as much I can. ddt of t square plus ddt of 10. So it becomes 2 times 1, the derivative, 4 times t square, x to the power n, its derivative is nx to the power n minus 1. So it becomes 2t to the power 2 minus 1. I already mentioned this here. The basic derivatives. Oops. Here it should have been if y equal x to the power n, it's the most basic. Oh, I already did that. Here. Sorry, it's there. Yeah, it's there. Like this. If y equals to x to the power n, then dy dx derivative would be nx to the power n minus 1. That's the key feature we want to learn right now. So the derivative of this thing, the 2 comes forward and the power becomes 2 minus 1 plus ddt of 10. A derivative of constant term alone is 0. Let's mark it here in the derivative part where we took the note. Where has it gone? Yes, here it is in this page where we wrote a few basic theorems. This is one of the fundamental results in derivative. d dx of any constant term is 0. So if the constant term remains multiplied with a function, then the constant term goes out of the derivative sign. But if the constant term is alone there, its derivative is taken to be 0. We are using these results. So the derivative would be 2 minus 8t at t equals to 2. So it's 2 minus 8 times 2, that is 14 with a negative sign meter per second. That's the velocity of the particle at t equal to 2 seconds. Another question on instantaneous velocity might be this: when does it stop? When does the particle? You can say the particle stops when instantaneous velocity is 0. Everything has instantaneous velocity 0 as it stops. So the dx upon dt is 0 because velocity is dx by dt. So the derivative I completed in this line here, 2 minus 8t was the derivative, this value. So straightforward you can say 2 minus 8t would be 0. So t would be equal to 2 by 8, that is 1 by 4 second. So at 1 by 4 second the particle was at rest. It stopped. Next question, one more question. Suppose velocity of a particle varying with time is given by this equation. By this shape, straight line. Vt curve of a particle is a straight line. So this point say is 10, 0. This is 0, 0. And this point say 0, 6. Where velocity is measured in meter per second, time is measured in second. You have to find acceleration of the body. What is the acceleration? So the solution can be like that. Since we have a Vt curve and the intercepts of time and velocity axis are given, we can use this equation for the straight line. Look at this equation, x by a plus y by b equals to 1, this format. If a straight line assumes this form, x by a plus y by b equals to 1, then the straight line intercepts x-axis at a, 0 and y-axis at 0, b. We use this concept for our question. So here you can write the x by x intercept a is 10. See, the curve cuts. If the equation of straight line is this, x by a plus y by b equal to 1, then a is x intercept and b is y intercept. Here the horizontal axis is t instead of x and a is 0. Similarly, the vertical axis is b instead of y, so b is 6. So just put it in this equation. So x means t here, so t to 10 plus y means b here. So b axis b divided by 6 is 1. So b by 6 equal to 1 minus t by 10. So b equal to 6 minus 6 by 10t, 60 by 10. 60 by 10 means 3t by 5. So instantaneous acceleration A is dv by dt, which is d dt of 6 minus 3 by 5 is a constant, so d dt of t. Now d dt of 6 would be 0, a constant, 3 by 5 into dt by dt 1. So acceleration is minus 3 by 5 meter per second square. And you can say that this acceleration is constant. So now if they ask what is the instantaneous acceleration, you say that is minus 3 by 5 meter per second square. If they ask you what is the retardation, you say 3 by 5 meter per second square, because retardation means negative acceleration. Negative sign is already considered during writing the term retardation. If they ask you what is the average acceleration, that is also minus 3 by 5 meter per second square, because the acceleration is constant. If a variable is constant, if value of y equal to say constant, then the instantaneous value of y will be same as its average value. Okay, so that's how we deal with the calculus and the coordinate. This question is a perfect example of how to blend coordinate geometry with calculus. First we used coordinate geometry to find the VT relation, velocity time relation. Then we used the concept of calculus to find the velocity acceleration relation, that is acceleration equals to dv upon dt. Now one more question where we have to employ the concepts of integration. Say Vt curve is given, velocity is given in meter per second, time is given in second. This is the velocity time curve of a particle. Here t equal to 2 seconds, here t equals to 8 seconds. You have to find displacement of the particle between 2 to 8 seconds. How much the particle has traveled between 2 to 8 seconds. That what is the displacement? The solution requires this knowledge. You can see that dx by dt is v. So integral of dx would be integral of v dt. Integration is the reverse process of differentiation. So if dx is equal to dx by dt is v, then integral dx is integral of v dt. Now integral dx means the total change in position, which is the displacement s. It would be integral of v dt. But integral of v dt means the area of vt curve equals to the vt curve area. So this area will give us the displacement as we see. So if the values are given in proper ways, you can find it very clearly. Say here the velocity is 20, I don't know, and here the velocity is 40. So the required displacement would be the area of the trapezium. Say the trapezium is A, B, C, D. The area of A, B, C, D. Area of trapezium, I will mention the formula beside. Area of trapezium. Suppose the parallel sides of a trapezium has lengths A and B, and distance between the parallel sides is h. This is called height of the trapezium. So its area is given by the formula half times sum of parallel sides times the height. So here we can employ this to find out the displacement, which is half times sum of parallel sides. One is this side, that is 20, plus other is that side, that is 40, times the height, means the separation between these two sides, which is between t to 2 to t equals to 8, that is 6 units. So this is 60 times 3, 180 meters. So we have given only one example for each of the topic that we have learned. For the next part, we will continue our discussion and show you more of these graphs, and we will discuss a few more variety. So today we have learned only the basics of coordinate geometry and differentiation, the calculus. Next day, we will continue with this into our part 2 and give you a few more examples on this. So let's continue to the next class. We will continue from where we have ended the next class. So wait for the next class and wait for our video part 2. Don't forget to watch it and subscribe for us to show the part 2. Your feedback will encourage us. Thank you.